Hi there, today we'll look at deep residual learning for image recognition by Kaiming He, Xiangyu Cheng, Shaoqing Ren, and Jian Sun. So this, you know it, this is an old paper. It is from 2015, but I thought we'd still look at it because this, not only is it one of the most influential papers in modern deep learning, it is also a very well-written paper. And I remember it like it was yesterday when this came out. This was like a bomb. So around that time, this meme was going around. I was winning ImageNet, but then someone made a deeper net. This was at the time when, after AlexNet, people were trying to build bigger and bigger networks, and every time someone managed to build a bigger network, the accuracy on the ImageNet dataset would increase. Pretty much in lockstep with how much bigger the network was. But people got to the limit of building big networks, and then this paper drops and changed everything. And now residual connections are everywhere, not only in image recognition, they are in transformers, they are in wherever you go, you'll probably find some residual connections somewhere in there. So yeah, let's look at this paper and let's revisit what kind of problems people had then and how they solved it. So here they go directly into this problem of deep neural networks. And the problem that people had was they knew that if you can increase the depth of a neural network, you can make it perform better, you can make it generalize better, you can reach lower training loss, but optimizing it was hard. Specifically, this was a phenomenon that people observed. So if you have a 20-layer neural network, you could train it, and there's this learning rate drop. People had already figured out that you need to drop the learning rate, and it would reach a certain level. And here, this would be the test error over here. However, if after a certain point, if they increase the depth even more, the training error would actually go up again, and so would the test error. And this is not a problem of overfitting, because overfitting would be when the training error is lower or as low, and then the test error went up. So this is the first thing. This is not a phenomenon of overfitting, of too many parameters. So why can't we train bigger layers? Networks until that time have very much followed kind of the original network design that was envisioned by sort of people like Yann LeCun and also AlexNet. And the most popular ones were these VGG nets. And they were very much of the philosophy that you'd have like you have the image here, and you input that into convolutional layers, which first would kind of keep a big resolution, but would increase the channel size by some amount, and then you would sort of downscale the image as you increase the number of filters. So you would stack more and more filters. I'm going to draw more filters. You would stack more and more filters while downscaling the resolution of the image. The reasoning was that if you do image classification, right, then where on this, maybe you want to classify this into a Lego tower or whatever that is. It's not that important where it is. So on the lower levels, you would want to parse out like very low layer features like edges and so on. And these are still important where they are, right? The fact that here's an edge, here's an edge, here's an edge. But then as you go higher up and go to more and more abstractive features, and we already knew that these neural networks, they tend to learn more and more abstract features as you go up the layers. The hypothesis was that the exact localization of these abstract features would be less and less important. So if you recognize that there's a rectangle, it's not that important where it is, just that it's somewhere there and maybe where it is in relation to the others. So if you want to recognize a car, the lower layers would recognize the fact that there are edges, and then the intermediate layers would recognize the geometric shapes of maybe here the wheels and these bodies. But it's not that important where exactly they are, and then the higher layers would learn to combine the individual parts to each other. And again, it becomes less and less important where these things are, and more important that you build more expressive features. So people would downscale the resolution, upscale the number of filters. Now that's a good heuristic, but this was basically the architecture of these networks. And we would question why would, if we increase the number of layers, so if we, instead of 1 here, we have 2 of these layers, right? We simply have 2 of these layers, and here we have 2 of these layers. Why does it get worse? Especially this paper here makes an interesting observation. So it is not caused by overfitting, and adding more layers leads to a higher training error. The degradation indicates that not all systems are similarly easy to optimize. Let us consider a shallower architecture and its deeper counterparts that adds more layers onto it. There exists a solution by construction to the deeper model. The added layers are identity mapping, and the other layers are copied from the learned shallower model. So pretty easy. If you have a shallow model, like 5 layers, that learns a particular function, I can pretty easily prove that there is a deep model that learns the same function by simply copying over these 5 layers and having these here learn the identity function. Okay, so if we're able to learn this, we should be able to train this network to at least the same accuracy. That's what this paper argues, because it can, these layers can simply learn the identity function. So it must have something to do with the easiness of optimizing these deep architectures, not with overfitting. And this is, I think if you read the entire text here, it's very, very clear. If you read it, they lead you through this reasoning saying that, look, all these layers have to do is learn the identity function, and then we could at least get the same accuracy. So why don't they learn the identity function? Well, because we initialize most weights, towards 0. We initialize them randomly, but mostly we initialize them around 0. Our initialization procedure, usually sample from some Gaussian with some kind of a standard deviation, but around the mean of 0. And also if we use things like weight decay, L2 regularization, all of these things, they bias the weights towards 0. So if there is any natural thing that these networks are good at, is they learn the 0 function really well. Learning the identity function is as difficult as learning any other function. The identity function in a convolutional filter is actually pretty difficult to learn, because if I have my 3x3 filter, where is my if I have my 3x3 filter, the identity function is like a 1 here and zeros everywhere else. That would be one of the things. It's not that easy. You need to learn 9 weights in the correct way. So this paper says, can we do something to make the default function of the network not be the 0 function or whatever the randomly initialized function? Can we make the default function the 1 function? Can we make the default function the identity function? And that brings you to residual connection. So instead of learning to transform x via a neural network into x, which is the identity function, why don't we have x stay x and then learn whatever we need to change? Okay, so let's call that tilde. If the assumption is that it's a good default to not change much, so this is almost the same as this, we might build this directly into the architecture, the fact that these two are equal plus some deviation that is learned right here. And the hypothesis is that especially the deeper you go, if you go very deep, each function here will actually learn not that much. It will learn to basically change the signal a little bit, but mostly it will learn the identity function if it behaves well. And therefore, it might be, reasonable to build this into the architecture. And of course, this has turned out to be very accurate. It has actually been reasonable to build this into the architecture. So that's what they propose right here. So instead of just having weight layers one after another, what they propose is to have these skip connections in here. So these skip connections, they will, instead of learning the function, they call this entire function h of x, which might be very complicated, they learn the function whatever f, and f is whatever you need to change about x. You see, at the end, you add x to it. So these weight layers here, they simply learn whatever makes this output different from this input. And learning differences, now you have the desired property, because what do we know about weight layers from before? Well, they tend towards the zero function, right? If we use weight decay or generally how we initialize them, they tend towards the zero function. Well, if f tends towards the zero function, then h becomes the identity function. So the default function of this network is the identity function. And whenever we learn something, we learn how to deviate from the identity function, and that is a much better default function. Now, it's not entirely true that the default function is the identity function. You see that here, for example, there's after the skip connection, there is actually a ReLU. So it's still a nonlinear function in total, the network in total. But the default for the individual blocks here is the identity. Okay. Now, if you chain these blocks, you get a residual network, and that's what they propose right here. So on the left, you see this original VGG architecture like we described it. So you can see you have an image which has 4 channels, and you first up it to 64 channels. And you keep the resolution, and then you max pool, which halves the resolution, but you go up with the filters to 128, you max pool again, go up with the filters, and so on. Now this has, even though it doesn't look like it, this has a lot of parameters, and it needs a lot of computation. So it has 19.6 billion floating point operation for a forward pass. In contrast, the networks we're going to build here, the residual networks, have 3.6 billion flops. So they are much, much less in terms of complexity than the old VGG networks, while still being much deeper. Okay, the hypothesis is the deeper, the better. And as a trade-off, per layer, you don't actually need to have that many parameters, because you don't learn that much per layer, but the succession of layers gains you much more than simply having single massive layers. You can see at the same size of resolution here, the ResNets can get away with much less amounts of filters, and that's why they are of less size. So this is the comparison, the VGG19. Now they do build this 34-layer network, which they call plane, and you can see it is simply a 34-layer network with pooling right here. And here, instead of pooling, they do a stride to convolution, which has also become this has become kind of more standard than doing max or average pooling to downscale, to do simply stride to convolution. So this paper has actually set the standards for a lot of things in modern deep learning. So our goal is going to be to compare, first of all, the VGG19 to the 34-layer plane, to show that you lose performance when you simply up the number of layers. But then when you introduce the residual connections, as you can see right here, so there is always this jumping connection right here. So along these jumping connections, the signal can travel as the identity function. What we're going to see is that if we go from plane to residual, introducing no extra parameters, just these skip connections, will change everything, will make this network all of a sudden trainable, and make the deeper networks the better networks. Okay, the only little caveat here is, of course, in order to build a residual connection, the output has to be of the same size as the input, because you need to add the input to the output. And this here, for example, is not given. So here you can see this signal after this layer is going to be half as big because it's a stride 2 convolution. So the output right here is only half the size, but it is twice the number of filters. You can see right here, this has 64 filters, and here we go to 128 filters. That's why this connection right here has parameters in order to simply expand the number of filters. These are these 1-by-1 convolutions that simply project the 64 filters to 128 filters. However, this doesn't introduce too many parameters because it's only 1-by-1. In fact, here the 34 parameters residual network. No, I'm wrong. You have different options. So the world has ended up at the option of doing 1-by-1 convolutions, but in this paper they still explore 3 different options. And I guess here in this particular experiment, option A is simply to 0 pad, so to leave the first 64 channels, but to simply append 128 0 padded filters there, or channels. Option B is the 1-by-1 convolution, and option C is actually that all of these connections right here also have the 1-by-1 convolutions, which introduces extra parameters. And they realize that option C isn't improving over option B substantially, and in fact is only improving marginally. And they say, okay, that's probably just because we have more parameters. So ultimately they went with option B, and I think that's what the world does right now. When I read this first, I particularly enjoyed this paragraph right here. Let's read it together. Our implementation for ImageNet follows the practice in The image is resized with its shorter randomly sampled in this. For scale augmentation, this crop is randomly sampled from the image or its horizontal flip with the per pixelized mean subtracted. The standard color augmentation is used. We adopt the batch normalization right after each convolution before activation. Ooh, an age-old discussion was born. When to use batch normalization, before the activation or after the activation. I think people are still fighting over this today. We initialize the weights as in 13 and train all plain residual nets from scratch. Use SGD, yada, 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 yada. The learning rate starts from this, is divided by then. So here in this paragraph, they detail basically all the training procedure and all the tricks that they use. And I remember specifically that, I've read all of this, which was the idea, and I could follow like, oh, this is super well explained, this is so cool, and so on. And then I expect basically an implementation of that. And then there's one single paragraph with like 20 lines saying, oh, and by the way, we use these 50 tricks from these other papers. And yeah, that's when it was already happening. You needed to do all the modern tricks in order to really reach the top accuracies. But in hindsight, we know it wasn't the tricks that helped them. It was actually their idea. I just thought it was rather funny. So you can see right here the results of this. If you look at the left, these are the plane networks, and we've already sort of seen this. Now this is on ImageNet right here. You can see the 18-layer network simply has lower train and validation accuracy. So the solid line here is the validation. On ImageNet, bold curves denote validation error of the center crops. So I guess they do center crops. So the training error is going to be higher because they do these different augmentations. But you can see the training and the validation error are higher in the deeper network if you don't use residual connections. Again, this is not due to overfitting, and this is because we can't train these deep networks, because we should be able to. the solution space of the 18-layer network is a subspace of the solution space of the 34-layer network. Everything tells us we should be able to learn the 34 layers to at least the accuracy of the 18 layers, but we can't. However, introduce residual connections, bum, 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 and you can see that the trend is exactly reversed. Now the 34 layer with residual connections has a much, much lower training and validation error than the 18 layer. In fact, look at this table right here. If you introduce the residual connections to the 18 layers, it's marginally better. However, if you introduce the residual connections to the 34 layers, it is a lot better. And this is another testament to the fact that these residual connections, they really help more and more the deeper you go. You can see the effect in, so this 18 layers, this is sort of a VGG19 depth network, while and there, we already know we can train these without residual connections, right? Because we were able to train VGG19. However, if we go higher to more layers, these residual connections all of a sudden make it a lot better. You can see that it's not that we can't train the 34 layers, but the residual connections just help a lot more. And most importantly, they don't degrade the performance from the shallower network. So they explore the different options right here and compare it to others. Different options, as I said, being A, B, and C, where A is the zero padding for the projection. B is having projections simply between where the channels don't fit, and C being having projections in every single residual connection. And you can see right here that the option B gives you quite a bit of a boost, while option C doesn't give you that much of a boost, introduces many more parameters, and overall I guess they decided against it, which since then the world has also decided against it. They also do deeper networks. So they built deeper networks like 50-layer ResNet, 101-layer ResNet, and 152-layer ResNet. And the 152-layer ResNet ended up being the best one, as you can see here. And you can see a pretty gain, like it almost lockstep gain. Depth, more depth means better network. And this, at the time, these numbers, they were unheard of. Like even 50-layer deep neural network was bombastic, but 152 layers, it was crazy. And the fact that still it has less parameters than the VGG19 and performs better, that was mind-blowing, absolutely mind-blowing. And then at the end they built an ensemble of these models and ended up taking the 2015 ImageNet competition winner. That was still like very important back then. It was still very important who wins ImageNet that year, where I think I haven't even followed up on the last few years. It's some kind of wide fixed ResNet whatnot with pre-trained and 50 billion extra data. So for the deeper networks, they decide that they are computationally become rather expensive. So they introduce these bottleneck blocks here on the right, where, as you can see, so here, if you have a 64-dimensional input, you do 64 feature channels in your convolution, have a 64-dimensional output. You can save computation if you first project the higher. So here you have a 256-dimensional input, and they say we can save computational power by pretty much projecting down to 64 first, because then our complexity of this layer, which is the expensive layer, will be the same as the complexity of one of these layers. And then we can project up again. The 1x1 convolution, they are significantly lower computational intensive than the 3x3 convolutions. Like it's 9 times less operations if you think about it. So that's what they use to build the deeper residual networks. And these residual networks, the ResNet 50, 101, 152, they are still staples today. You can have These are, you can have pre-trained versions of those and people still use it. Like ResNet 50 is used in every segmentation whatnot application. So yeah, this has turned out, these decisions here have, made it long way. Here you can see the number of parameters in these residual networks. And this was the absolute craziest thing right here. 1,202 layers, okay? So you can see still until here, ResNet 110. Now this is on CFAR 10 right here, not on ImageNet anymore. But you can see that even 110 layers still had less parameters, or actually this, like the same order of parameters than these previous networks that were only 19 layers deep. This was unheard of, and much more unheard of, 1,202 layer network to train on CFAR 10. It's a bit of an overkill, but they say their goal was explicitly to study depth. And you can see here that with the deeper and deeper networks, they outperformed all of the previous networks, so all of the baselines and themselves as they went deeper and deeper and deeper. However, once you go to 1,002 layers, you go up again. So here's the question. Was this all just kind of a trick, a hack, and do we run into the same problem again? And that's the question they ask themselves. And the answer is no. So if you look right here, so here you see again the plane networks. In the plane networks, you can pretty easily see that the more layers you have, the higher your error goes. Whereas in the residual network, it's exactly the opposite way. The more layers you have, the lower your error. And if you compare this 110 layer network with the 1,200 layer network, you see your validation error going up again. However, your training error, and I can't zoom in more, but it's the same. It's the same, and it's at 0. So here they conclude, and here they conclude, now we are overfitting. They don't use like the biggest data augmentation like we use today, so overfitting was still a thing back then. So now they conclude, okay, now we have actually built a large enough network that is overfitting, and the fact that we go up again in the training error is due to the fact that we are probably overfitting. So not only have they enabled us to build deeper networks, they have effectively shown that this can get you to the point where you don't need deeper networks anymore, at least on CFAR 10, because you are overfitting. And it can effectively get you there. This is a lot of evidence for the fact that this biasing the networks towards the identity function is a very valid thing to do, and is the solution to the we can't train deep networks problems. Lastly, they investigate the size of the responses. So their hypothesis is that if it is really beneficial to bias the network towards the identity function, and if it is really true that each of these layers only learns a little bit, right? Because the identity function is already very good, each of these layers only needs to learn kind of a small function. They look at the responses of these things. So the response magnitude of these layers right here, of the signal through the layers, and they compare those with the response magnitude of the other neural networks where you don't have the skip connection. The hypothesis is if we look at these, then the responses of these layers should be much larger because they have to learn much more, and the responses here will be much smaller because the identity function is already doing most of the work. And that's exactly what you find. So here the layers are ordered by response, and you can see the plane networks in the dashed lines are significantly above the residual network. And that's not a function of the depth, because if the depth was actually equal here, you would expect that the dashed lines would stretch like this, right? They would kind of stretch out. However, exactly the opposite is happening. you can see that the residual networks, even at the beginning, their responses are very much smaller. And this is kind of what I like about this paper. It's one narrative. It is a hypothesis, and then every single, like the hypothesis is taken, and they make predictions from the hypothesis. They say, okay, if we are right with our hypothesis, not only should our idea get us better accuracy, that's what most papers do today, but also, it should be that we can, for example, push our network to the brink of where we actually are overfitting, like here. And it should also be that the responses of our signal through our layers is smaller. Research like this is just pretty cool, and it's, I think, a lesson for us that sadly the world has taken the ResNets, but the world hasn't all taken the research methodology of this paper. If you want a good read, it's very well written. I'm very sure you can follow it even if you have read very few papers. And with that, I hope you enjoyed this. Please tell me what you think of going through kind of old papers, looking at whether or not they have stood the test of time, and any other comments. Leave them in the comments. I do read them, and I'll see you next time. Bye-bye.